Has anybody found the first stage yet? I know one person has. A couple of people. All right. Well, just having some DNS issues, so it'll work in a minute, I hope. Whenever the
All right. All right, I'm Seth Hitefield. I'm one of Dr. Clancy's PhD students at the Hume Center at Virginia Tech. So I started doing stuff with GNU Radio about 2 years ago. And so recently we just finished up a project looking at using GPUs to do some acceleration. So I'll be talking about using custom buffers to help integrate GPUs into a flow graph and to make it much easier for development using GPUs. So first of all, GPUs, as Dr. Clancy talked about a little bit earlier, massive parallel architecture. You know, they're based on the single instruction, multiple data architecture. So you have, you know, on things like the Titan X, you have thousands of cores. The latest Titan X, the Pascal architecture has, you know, 28 individual multiprocessors, each one 128 cores. So you're looking at, you know, 3,500 cores on a discrete card. When you combine all those into something like the NVIDIA Digits Dev Box, you can have upwards of 28 teraflops of power, you know, sitting on a desk. Also, they've been doing a lot of work with embedded systems, so things like the Tegra X1, that's their top-of-the-line mobile processor, and it has 2 different SMs, so about 256 cores on there. And you know, it's all easily programmable with CUDA. So, you know, over the past few years, this is one of the graphs that they have from the CUDA developer guide, and you can see that, you know, the GPU theoretical power has, you know, just exploded over the, you know, past 10 years. So that makes it a very interesting candidate for doing in acceleration with flow graphs. So, you know, there's a lot of operations in DSP that are parallelizable. You know, for example, just adding 2 signals together is, you know, if you just add those 2 samples, each of those can be done independently in the thread. And the problem, though, is you do end up with latency, right? Because you have to wait a long time for enough samples to buffer up before you can actually make use of these parallel architectures. There's been a lot of work already been done with bulk and a lot of hardware extensions, you know, Intel with SSE, AVX, and ARM. I think Doug's going to be talking about neon acceleration a little bit later today or tomorrow or something. So yeah, there's a lot of work with bulk doing and you know, exploiting these parallel architectures in CPUs for acceleration. But when you start working with GPUs, there's a whole different ballgame, because with the CUDA programming model, and I'll be talking about CUDA because all the stuff that we've done is on the NVIDIA processors, but all of this can very easily be transferred over to things like OpenCL. So when you start talking about GPU programming, it differs slightly from what a traditional CPU algorithm, right? So you have individual threads, and those threads are very similar to the traditional definition of a thread that you would find with CPUs, except they're scheduled very differently. For example, with the GPU, you are scheduling groups of threads that run in parallel. So when you create a specialized CUDA function, you have to take into consideration things like branching, memory accesses, and those types of concepts, because if you start having branching going on within a kernel, you end up underutilizing the GPU, because half of the system is doing one half of the branching and it has to wait for the other or let me, if you have branching with like an if statement and it's each other thread is doing something, only half of the GPU is working at any given time. So when you start scheduling things, you have to take these into consideration. Also, there's a lot of overhead involved with scheduling kernels. So for example, I ran an empty kernel, and I was testing it with multiple different thread sizes. And you can see that it took anywhere from 48 microseconds to 183 microseconds just to run an empty flow graph. Now, that's not a lot of time, but when you start integrating it into a DSP application where you're running multiple kernels over and over within a given time period, that can significantly add up and cause a huge amount of overhead and just kill your performance. So another thing that you have to take into account when dealing with GPUs is memory management. So every single framework for GPUs has to allocate its own memory. You can't use traditional methods like malloc. And this is simply to ensure that the GPU has access to whatever memory you're actually trying to use. So for example, with CUDA, you have to use the CUDA host alloc or CUDA alloc in order to allocate those buffers, which you then can use for your kernels. That causes an issue, though, because within GNU Radio, the scheduler allocates all of the output buffers for the output ports. So for every single block with all the ports, you have a buffer that gets allocated, and that buffer gets passed to the downstream block to read from. With CUDA, trying to integrate this, it means that what you would have to do is copy all of your samples from your output buffer on an upstream port into a CUDA buffer before you can execute the kernel. And then once you execute the kernel, you have to copy memory from the CUDA buffer back to a GPU buffer, or excuse me, back to the host buffer. So you have a double memory copy that's going to have to happen for every single kernel execution in a GPU block. And this is going to cause a huge amount of overhead. So there's been a little bit of work from the University of Maryland trying to get past this limitation. And what they did is they had these two new blocks, host to device and device to host. And these two blocks would handle memory transfers and allocating buffers on the GPU, which then can be used by other blocks running in the system. And what they would do is whenever samples would come into the host to device block, it would manage a transfer to the device. And then once that is in device memory, the GNU radio allocated buffers would be used to transfer pointers between the blocks. There's the one problem with this, though, is it changes the underlying model of the flow graph. Because with a flow graph, the pointers that are given for every work function are pointing to the actual data. So now you have basically two different sets of buffers that you have to worry about and translating between those when you're trying to execute kernels on the GPU. So the goal of the custom buffers work is to allow blocks to allocate their own specialized memory. So for example, with CUDA, whenever a block gets constructed, it can tell the scheduler that it needs to handle its own memory. So in this situation, the block can allocate two different buffers, which GNU Radio then manages, and passes those buffers to both the upstream and downstream blocks in the flow graph. So the upstream and downstream blocks write directly to whatever memory had been specified by the block with that allocated the custom buffers. So that requires some additional changes to the runtime. So for example, there's new flags that you use when you are creating your input-output signatures to tell the scheduler that you need to allocate. So there's the memblock alloc flag. And there's two virtual functions, allocate output buffer and allocate upstream output buffer. And these are the two functions that a block needs to implement in order for the scheduler to call to allocate the buffers that it then uses. So one of the other things that this causes is an issue with double versus single map memory buffers. So in the GNU Radio runtime, every single buffer that is allocated is a doubly mapped virtual memory circular buffer. So in this flow graph, or excuse me, in this figure on the right, what this represents is there's twice the buffer size is actually allocated. And the second half of the buffer is demapped and mapped back to the original first half of the buffer in virtual memory. So what this does is it simplifies a lot of the code that is needed for the scheduler, and it makes implementing things like sample history much, much easier. So for example, for a work call, the scheduler no longer needs to worry about where the end of the buffer is. It can simply tell a block you have 8K items, and when the block starts writing, if it exceeds the first half of the buffer, the mapping ends up wrapping all the way back around and writing at the very beginning of the buffer as well. So when you're dealing with custom allocated buffers on specialized devices, this double mapping may not be supported. So the buffer has to take into account special cases, corner cases, to ensure that any pointers and any buffer space that is passed to the work function is valid. Otherwise, you don't want a block to accidentally crash when it writes outside a buffer. So these are all things that the scheduler guarantees that you have to take into consideration when dealing and writing a custom buffer. So this is a quick example of a flow graph and kind of the concept of what this custom buffer does. So in this case, we have a null source to a multiply constant, which is using a CUDA implementation to a null sink. And the allocate upstream output buffer and allocate output buffers allow this block to allocate these two CUDA page-locked memory buffers, which means that these buffers are now accessible to the GPU. And they're also accessible to the host. So in this case, the null source can write directly to this CUDA buffer, and that CUDA buffer can be directly read by the GPU. There's no explicit memory copy that needs to happen from the GNU radio buffer to the CUDA buffer. So for some performance tests, I used a very, very simple flow graph. The goal of this was to see what kind of overhead we were saving by using the custom buffers. So we're trying to measure the maximum throughput. We were not really concerned about other things like back pressure, hardware rates. The goal was simply to run as fast as possible to see what kind of advantage the custom buffer will give you with the GPU over existing techniques like Volk. So I had 5 different implementations. A generic implementation of the multiply constant block. It just ran a for loop, no optimization there. The multiply const complex to complex block, which uses one of the Volt kernels. And then we had 2 different CUDA implementations. One of them that used a memory copy, and it had to copy from a GNU radio buffer to a CUDA buffer before it could execute the kernel. And then the custom buffer version of the CUDA graph. And on the right here, this is an example of an empty flow graph. So in this case, this is a null to null block. Completely pointless flow graph, but the purpose of this was to look at the overhead of the GNU radio scheduler itself to see what the upper bound would be without anything in the system. So as you can see, so each test used doubled the buffer size of the previous test. So as expected, the performance of the the empty kernel doubled every single time it ran, which kind of makes sense because you're doing twice the work for every work function, so you have half the overhead. And at the very, very bottom, it's very difficult to see, but that's a comparison of the generic implementation. So you can see here that it's quite obvious that the actual multiply constant operation is what's causing a lot of the overhead. So to compare the different implementations, here we have a plot here on the left. The 2 in the middle are the generic implementation and the Volk implementation. And the Volk implementation gave anywhere from a 20 to 50 megasample per second increase in performance and maximum throughput over the generic implementation. But both of them maxed out close to about 450 megasamples per second, even with the increasing buffer sizes. The green one at the very bottom is the CUDA implementation with the memory copy. So you can see very clearly that the memory copy is causing significant performance loss on this. And on the right, that's a comparison between the same exact flow graph, one of them where it's actually executing the CUDA kernel, and the second one where it's not. So that comparison shows that the memory copy is what's causing a significant amount of overhead there. And the custom buffer version would be the red line. And its performance is pretty interesting because at the very beginning, it actually performs poorly in comparison to the rest of the implementation, specifically the generic one and the bulk one. And this has to do with I talked about it before, the overhead from the kernel launches. In this situation, you're dealing with a very small buffer size, which means that your number of launches you have a much higher number of kernel launches in order to execute for a given time. So as you increase the buffer size, you're cutting down on that overhead significantly. And the CUDA version is able to get about 166% performance increase over the bulk and the generic implementations. But the trade-off is that you have more latency. You have to increase the buffer size by 128 times to see that type of performance. So you have much higher throughput, but you have a much higher latency as well. So we're able to see that with the CUDA block with the custom buffers. We're able to get, like I said, about 166% increase. And the throughput that we were getting was about a gigasample per second versus about 450 megasamples per second for the CUDA, or excuse me, the bulk block. So that's all I have. Anybody have any questions?
Could you go back a couple slides?
Sure.
Okay, one more. Okay, so there, go forward. Buffer multiplier, is that the buffer size that you're doing in one kernel?
The buffer multiplier is, it's the buffer size. So I started with a base size of 8,192 samples, which is what on the system I was doing testing on, the Tegra X1. That was the default size for the GNU radio buffer. And I just multiply it by power of 2, so doubled it for each test.
Okay, so another thing that is kind of hidden in the way you use CUDA, memcopy and the CUDA host alloc, you're moving the memory from one device to the other regardless. A lot of it is, in other words, there's no memory mapping between that PCI card and the other. It's a matter of whether you do it manually or whether you let the code that CUDA provides do it under the wrappers for you in a more optimized way.
So in this case, and I'm glad you asked that, I forgot to mention that all these tests were being run on the Tegra X1. Mm-hmm. And the Tegra X1 is an integrated
that's
platform,
the shared memory,
which uses shared memory.
So that's
in this
totally
situation,
different.
there wasn't a copy.
That's a totally different ball game.
Yeah,
there.
I forgot.
So that changes the metrics of this completely. I think most people will end up using the PCI card version, and thus this memory issue becomes much more important.
Yeah,
and there you need to distinguish, like I say, the mem copy and the custom buffer on the PCI card setup. You're moving the memory from one device to the other regardless. It's just under the wrappers, CUDA is doing it for you in the one case, and the other case, you're making decisions to do it manually. So you have to be smart. CUDA has those built-in smarts to do it properly. But I think, well, we can't really discuss it in these terms. This is a Tegra. This slide is showing Tegra. So it's a different ball game. for people who don't know, the Tegra has true shared memory. They have one physical set of memory, and both the GPU and the CPU map to that same physical memory. Whereas with any of the GPU cards, it's sitting on the PCI bus, and it's two physically separate pieces of memory. Something I have found, though, that would kind of look like this is when you are writing the code, the CUDA uses a DMA engine to move it. And increasing the buffer size is always a good thing because the DMA operations are much more efficient when you're moving large blocks of memory as opposed to the small blocks. I've tried using a variable, just an integer that I would move back and forth across the space to keep track of things, and that kills performance. So when you have a small thing, you need to be inventive and think out of the box about how to track that information on both sides without having to move it every time,
Right.
Which can make sometimes very much more convoluted code. Anyways, in a nutshell.
All right. Are there any other questions for Seth? I got one.
The multiply const is obviously not the most complicated block that a lot of people have looked at. Have you done any benchmarking, or are you planning on doing any benchmarking of any more complicated functions?
Yeah, we, for the project that we were working on, we had a channelizer that was running on the Tegra board. And I think in comparison to the Volk Acceleration 1, if I remember correctly, we were hitting around 60 megasamples per second with the GPU. But of course, that had to deal also with a very large buffer size. And the same, or the GNU radio channelizer was around, I think, maybe 12 megasamples per second. But I wasn't sure if we were able to really show that or not. So,
but did you do any similar comparisons of how the buffer size, if there was a similar crossover point?
Size? I don't remember exactly what it was, but it was at the smaller buffer size. The GPU version was slower than Volk, I think. So, once you increase the buffer size, that's really where your performance is going to get much better. But of course, increasing the buffer size is going to cause much longer latency in your system.
Any other questions from the audience? No, so I have one, Seth. So we've been talking about leveraging coprocessors, offloading stuff from GNU radio flow graphs for years, right? I think we first launched this discussion in the Boston GRCon several years ago. So obviously, the work that you're doing now is you're using GPUs. How would you say this relates or maps or could be leveraged or will grow into being able to use other types of coprocessors?
Yeah, great question. So in this situation, with the custom buffers, we were just looking at GPUs just because that's what I was interested at this point. But there's nothing to stop using that writing a custom buffer that would support the Keystone 2 processor for TI, or writing a buffer that an FPGA could write directly to memory. So there's definitely many other types of coprocessors that you could use with a custom buffer. I just haven't gotten to the point of looking into those yet.
Any other questions from the audience? No? Okay, let's thank Seth. All right, so strangely, we are way ahead of schedule by 25 minutes. Yeah, so lunch is not served until 12:15, same place next door. And we pick the conference back up at 1. So we're just going to have an extended break here. So you have 25 minutes till lunch is served. Lunch will be out for 45 minutes, and we'll start back up here at 1 o'clock.